Good morning, students. I'm Professor Prasad. So we'll begin with the original topics of computer organization. So in module number one, we got two chapters. The first one is basic structure of computer, and second one is machine instructions and programs. So in basic structure of computer, we got some basic concepts like what exactly computer organization stand for. Okay, how many functional units we have, how we can connect those functional units so that we can make a better organization. Okay, regarding that also we have a complete study. Then the first topic is like basic operational concepts. Okay, this is very important topic. One fixed question from module number one, either in part A or part B. Fine. The marks may vary from 6 to 10. Okay, it depends. Okay, 6 to 10. They may ask 6 marks, 8 marks, or 10 marks. Basic operational concepts. Then bus structure. This is also a very important question. Fine. So this may be like 4 to 6 marks with figure you need to explain. Then regarding the performance, this is also for 6 marks question, right? They may ask you like what is processor clock, comma, then basic performance equation, clock rate. Okay, such kind definition they may ask for 2 marks. Okay. Then later second chapter, machine instruction and programs. Okay, so in this we need to study what exactly memory is or memory addresses are. Okay, how the instructions will be stored in your memory. Then if I want to read any instruction, then what is the procedure? What are the different methods of reading principles are available? Okay, regarding that we have the complete study over there. Then later we got some topics like stacks and queues, subroutine, then additional instruction. Okay, apart from the main instruction, we got 4 to 5 different additional instructions in our topics, okay, in our syllabus. So that we need to study. Later, encoding of machine instruction. There are a lot of encoding methods available. Okay, so what kind of encoding method is resided in our syllabus? Okay, we'll go through that. Fine. Okay, so we'll go to the first topics. Okay, computer types. So before we move on to the basic operational concept, first we'll study how many different types of computers are available. Okay, total 6 types we listed over here. The first one is personal computer. Okay, second is desktop computer, then notebook computer, then workstation. Okay, that will be utilized for high-end graphical input and output. Then the third one, servers or enterprise system for client-server communication. We are using this. Fine. And later, supercomputers. Okay, if you want to go for large-scale numerical calculation or else aircraft design or else weather forecasting. Okay, for finding the weather or else for predicting the weather conditions and all. Okay, then we need to go for supercomputers over there. Then what is this personal computer? Like one person can use at a time. That's it. Okay, we don't have a multiple user option over here. Okay, one person can utilize the resources of the computer at a time. That's it. Okay, so that will be called as a personal computer. Okay, the labs systems what we are available in our labs or PCs and all whatever we are using, like at a time one person can use. Okay, so that system we are considering it as personal computer. So the desktop computer is obvious. It will be rested over a table. Okay, that's why we are calling it as a desktop. Fine. Like monitor will be separate, then keyboard, mouse, everything will be separate over there. Then notebook computers here, entire structure of or else entire organization of your computer will be compact. Okay, like it will be like a monitor, keyboard, motherboard, input and output units, whatever we have in our desktop. Okay, that will be compressed and that will be compact under a single piece exactly. Okay, like our laptop or else notebook computers means the tabs and all. Okay, so these are all we consider it as notebook computers over there. Then later, workstation we have. What is this workstation? High-end graphical input and output. Okay, so this we are using for simulation purpose. Remember, okay, one best example is if you want to, or else if any car manufacturer want to launch any new brand or new model. Okay, so what they used to do is they don't simply manufacture the car. First, they go for the simulation. Okay, first they go for simulation. Okay, what kind of road grip we need to provide? What should be the gesture of the car? What should be the elevation of the car? What should be the design of the car? Okay, so these everything will be designed under the simulation. Okay, and we are going to test them based on the simulation fashion. Okay, instead of practically designing them. Okay, then what we need to do, we need to go for the simulation first. Okay, and we do it for network design also. Okay, we are having NC2NS. Okay, so some different kind of simulators available. Okay, in our network field also. Okay, so what we need to do, instead of going directly deploying the network for the particular area, what we need to do, we need to design the topology for the network. Okay, in case of simulation fashion. Okay, then later, if it work properly, if it work properly, that network topology, what we are designing in our simulation, okay, if it work properly, then physically we are going to implement that. Okay, for what reason it is? Okay, to avoid the losses. Okay, to avoid the failure, what we need to do, we need to go for simulation fashion first, then we need to go for the implementation. Remember, okay, in such kind of situation, we are using the workstation over here. Then later, server or enterprise system. Okay, so here, like client will be requesting for the resources to a system. Okay, a system which is providing the service for that request will be called as a server. Simple. Okay, like we are using different kind of a protocol. Okay, like the request fashion will be different. Okay, sometimes we may go for like based on a URL, it may be. Okay, any other different kind of requesting mode, it may be available over there. Okay, means client, if you consider me as a client, okay, if I want to access my Facebook profile, then what I need to do, I need to use a URL called as like www.facebook.com. Okay, when I type that facebook.com, okay, like I'm trying to hit the Facebook server over there. To the response of that, what I used to get is, I used to get a login page of a Facebook. So that is what the service provided by a system. Okay, that service provider system, we are considering it as what? Server. So inside that, lot many files are available. Okay, instead of maintaining all my photos, all my videos, all my text, okay, whatever I want to share in my profile and all, okay, instead of maintaining those data in my laptop or in my desktop, okay, what I need to do, I will be maintaining in some other system. Okay, so whenever I want, I can access them. Okay, so that second system, we can consider it as a server. Okay, who provide the entire service, whatever the client requires. Okay, and also we call it as enterprise system. Okay, so this will be used in the organization. Okay, for accessing the file, for managing the like large amount of information. Okay, in case of organization and all. Okay, in MNCs and all, we are using these kind of systems. So it will also act like a server itself. Okay, like the workers, they need to access different software which is available in their library. Okay, or else they will be working on some project. Okay, after completion of that project, if module wise we need to store it in some system. Okay, then later this another person, if I want to access that particular project or the same module, then he can get access from that system, that enterprise system we call it as. Okay, so this is like client and server communication. Okay, service provider will be there and service user will be there. Okay, between that, whatever the communication we have, okay, that we are calling it as server and the enterprise system. Then later, the last one, supercomputer we have. So the advantage of using supercomputer or application of using supercomputer will be what? Large scale numerical calculation and aircraft design. Okay, so if you are like if you are available with a lot of numerical inputs, okay, and if you want to process them, okay, large scale numerical inputs if you are having, and if you want to process them to get some fine result, okay, then what we need to do, we need to go for using supercomputers over there. The one best example is aircraft design. Okay, it is not so simple. Okay, it is not so simple to design the aircraft. We need to concentrate on a lot of context. Okay, like we need to go for a lot of scenarios. Fine. So we need to depend on some high-end computer. Okay, that we are calling it as supercomputer. And also we can use this supercomputer for weather prediction. Okay, so daily we used to get the updates like tomorrow it will be raining. Okay, so bring umbrellas, and Google update we used to get, right? Okay, regarding the climate, how they are going to predict. Okay, based on some inputs, what they get today. Okay, according to that, they will work on that using a supercomputer, and they will predict what will be the weather condition for tomorrow. Yeah, okay, I hope you don't have any doubt. Computer types, total 6 types we have mentioned with. Personal computer, single user it is. Desktop computer, yes, it is a single user, but we don't have a portable facility over here. It will be rested over a table. Notebook computer, yes, all those functional units, whatever we had in the desktop, okay, it will be compact under a single piece over there. That we are calling it as a notebook computer, which is having a portability facility. Clear? Then workstation, like which will help for graphical input and output kind, simulation fashion. Okay, server and enterprise system, it will act like a service provider, okay, for the clients, and later supercomputer. So large scale numerical calculation, if you want to perform, then supercomputers can be utilized over there. Then when it comes for computer organization, we need to study all the functional units to cover our entire syllabus. Okay, so these are all functional units, whatever we have. Okay, so that depends, like that is what your modules are. Okay, first module, second module, third module, fourth and fifth, exactly. Total 5 different functional units we got, 5 different modules we have. Okay, so in each and every module, we need to study about each and every individual functional units over here. Clear? Okay, fine. So here we got total 5 different functional units. The first one, input or output we consider. Okay, just observe here, input or output we are considering here. Okay, input unit and output unit. Okay, first and second. First will be input, second will be output, and third one is the memory over here. Okay, functional unit number 3, memory it is. Then fourth will be arithmetic logical unit. Fourth will be arithmetic logical unit, and fifth one will be control unit. Okay, so processor, okay, it consists of two main functional unit. One is what, arithmetic logical unit, and second is what, control unit exactly. Fine. Okay. Now, when it comes for discussion about the functional unit, first I would like to discuss about memory. Okay, because it takes a very important role in case of the execution of a task or the performance of the system exactly. Yeah. Now, when it comes for memory, okay, we used to get a picture like, yes, we have two different types of memory in our system. First one we call it as a primary, and second, secondary memory over there. Clear? Primary memory and secondary memory. What exactly this primary memory stand for? How it differ from the secondary memory? See, primary memory means a memory which is less in size, observe my words, which is less in size, having more potential to work. Okay, like the speed of work or speed of execution will be more in case of primary memory, and cost will be high, and also it is very close to the processor. Clear? A memory which is able to work in fast manner and which is very close to the processor, fine, those memory we are calling it as a primary memory. Fine. And later, what will be the secondary memory? Secondary memories are large in size, okay, less in cost, and the working speed will be less compared to the primary memory. Those memory we are calling it as secondary memory over there. Then, example for primary memory. Can you give any example for primary memory? Yes, ROM, okay, read-only memory, RAM, random access memory, then cache memory we call it as. Okay, so these are the three different memories. We are considering it as primary memories. Yeah, then what will be called as a secondary memory over there? According to our system, if I consider, okay, hard disk, fine, CD, fine, then later floppy disk, okay, then pen drive. So these are all we call it as what, secondary memories over there. Yeah, the memory which is close for the operation of a processor will be considered as a primary memory, and those we are like bit away from the processor, okay, we can consider as secondary memory over there. Okay, when we go through the module number 3, we have a complete discussion about primary memory separate, okay, secondary memory separate. What are the different memories are available, what is the working principle of those primary and secondary, what kind of medium we are using to store the information in primary and secondary. Clear? Okay, so that we will be discussing in module number 3 exactly. Okay, now for the time being, while discussing the memory, this is enough actually. Primary memory is a memory which is close to the processor and which is having a potential to work in fast fashion. Okay, but secondary memory are large in size, but the working will be bit slow. That's it. Okay, then later, here something we have called as a word length. Just observe here. Okay, we got something called as a word length. What exactly this word length stand for? Okay, so whenever we try to download any software, okay, like any software if you want to download, okay, then in your Google there will be like some particular software download, okay, but in front of that we used to get like 32-bit 64-bit, right? Did you observe that? For while downloading any software we used to get like 32-bit 64-bit. What exactly the 32-bit and 64-bit stand for? Okay, so that is what the memory arrangement what we have in our RAM or what we have in our primary storage, okay, means in one attempt how many bits your processor can read from the memory. Okay, that is nothing but the word length. I repeat, in one attempt, how many bits your processor can read or write from your memory, that is nothing but word length. Okay, if your operating system is 32-bit operating system, then the word length will be 32-bit. Means in one attempt, your processor is able to read 32-bit of information from the memory, or else 32-bit of information can be written into the memory word. Okay, that is what the word length stand for. Clear? Okay, so this is regarding the memory over there. Then arithmetic and logical unit. Okay, basically we consider like, yes, it perform arithmetic operation. Okay, no, yes, obviously it performs some arithmetic operation like addition, subtraction, multiplication, division, and also other arithmetic expressions or arithmetic operation. Let it be. Okay, but whether we are using this particular functional unit only for the arithmetic unit or arithmetic logical operation, or whether we are using it for other, yes, we do. Okay, see, if I want to read any memory location, sometime we need to add some values for the address of the memory location. Sometimes we need to subtract some value from the address of the memory over there. So in every access of the memory, we need arithmetic logical unit. Remember this. Okay, it is not only utilized for arithmetic expression. Remember this. Okay, a plus b. Okay, ALU unit will be utilized. No. Okay, not only for the arithmetic expression. Apart from that, reading the content from the memory or writing the content to the memory, okay, we are encountering operation of arithmetic logical unit over there. Clear? Memory over, arithmetic logical unit over. Then what exactly control unit stand for? See, here I had written like timing signal. See, control units, okay, we have something called as timing signal. What exactly this timing signal stand for? In bracket, we had written like read and write. Okay, the job of your control unit is to generate two signals. Okay, first one we call it as a read signal, and second one we call it as a write signal. Okay, so that is what we are calling it a timing signal. Okay, it depends on time. It depends on time. Okay, whether you are using if your processor is trying to read the content from the memory, then read signal will be generated. If it is trying to write the content to the memory, then write signal will be generated. According to the time, your control unit will generate either read or write operation over there. Clear? The complete operation, whatever we involved in our system is what? Either read or write. That's it. Okay. Apart from this, we are not doing anything. Okay. We need to read the content from some location, upload it for the processor, execute it. We will get the result. Then if you want to store the result, go to the memory, write it. Over. Okay. Only two operations we have, read and write exam. Then later, input unit and output unit, it's very simple. Okay, so these are all like input unit we are utilizing for grabbing the input from the user. Okay, what user want to express. Okay, for mentioning those expression, what we do, we are using input unit over here, then keyboard, mouse, then scanner, fine, joystick. So these are all the input unit. Okay, we can call touch screen, like it is, we are calling it as a dual. Okay, so it will act like a input and also it will act like a output, right? See, if I want to play any movie, what I need to do, I need to tap on my screen, okay, touch screen, or else mobile, right? Then it will play. Okay, then where it is going to play? In screen itself, right? Okay, input and output. We can consider the touch screen monitor or touch screen mobile. We are considering it as what? Input and output. Okay, both functionalities we have. Then in case of output, like monitor, then printer, then speakers. Okay, so these are all we consider it as output unit over here. Okay, the result should be shown for the user. Okay, so that will be considered as output unit. So I hope it is clear the functional units. Total 5 functional units we have: memory, arithmetic logical unit, control unit, input and output. So these three are very simple. Okay, control unit will generate only two signals, read and write. Okay, input unit will allow the user to enter the inputs. Okay, output unit, it will allow the user to see the output. That's it. Okay, then later arithmetic logical unit. Okay, it is utilized for arithmetic expression and also to read the memory content. Okay, fine. For finding the, or else instead of saying like reading the memory content, for finding the memory location, ALU can be utilized. Then later, when it comes for memory, primary memory we have, secondary memory we have, then later word length we have. So these are the few topics under functional units. Okay, next, very important concept, basic operational concepts. Okay, so in this, so we got some examples. See, example of executing one complete task. Example of completing one complete task. Okay, so now if I assign a task for third semester computer science student, okay, for writing a history, or else okay, fine, writing a history about the evolution of computer generation. Okay, if I say, okay, then what you are going to do, you are going to find some information from the Google, right? Okay, like what is first generation, second generation, third, fourth, fifth, okay, like that. So from where you will begin, you will begin with the first generation, obvious. Okay, we don't go for a flashback in case of a history, right? Okay, what we do, we are starting from first generation to fifth generation, right? Okay, so the assigned task was what? The history about the evolution of the computer, right? Then the student will start breaking them into a different pieces: first generation, second, third, fourth and fifth, like that. Here your computer, if it want to execute a complete task, okay, you can observe here, we got one complete task, let it be anything, okay, like one complete task we have. If I want to execute this particular task, what we need to do? We need to break this complete task into number of instructions. Observe it carefully. One complete task we have, it should be broken down into number of instructions over here. Okay. Individually, your processor will start executing each and every instruction. Okay, each and every instruction, starting from first line to end. Okay, if you are doing this like starting to end, what does it mean? Task done. Here, one particular task we had, example for adding two number, 4 plus 5. Okay, consider we have a task of adding 4 plus 5. What will be the result? 9 is the result. Fine. If I want to execute this, so that we are considering this a complete task. Okay. Now, if I want to programmatically execute this, what I need to do? I need to go for writing a C program. Right. I need to declare some variable. I need to go for a print statement. Right. Okay. And then I need to display the output. Okay. See, if I want to do so, then I need to go for writing different lines of programs over there. Those programs are nothing but the instruction what we are giving for our processor. Clear? Instruction is nothing but some indication or some information we are providing for the processor what he should perform. Okay, if that information in proper format, because system is expecting some set of syntax representation, proper syntax representation. Okay, if you are doing in a proper format, then easily it will be executed, and the task what you are willing to achieve, that will be done. Yeah, okay, this is how a complete task will be executed by your system. I hope you don't have any doubt, right? Okay, fine. Now, later, just observe, we got one more question. Fine. Like how to execute one instruction. See, in this I said, like complete one task will be broken down into what number of instructions over here. Then if your processor starting from the first instruction, and when it reaches the end, it will be called as task done. Okay, fine. Then how your processor is going to execute this one instruction? This is the big question, right? Okay, how it is going to execute this one instruction? And what is the syntax of the instruction? Whether it is like printf open bracket double quote open, okay, my name is Prasad double quote close, okay, whether this is what the syntax of the instruction what your processor is expecting. No, remember, okay, the programming languages whatever we are learning in computer science, okay, like C, it may be C++, it may be Java, JavaScript, okay, HTML, whatever it is, we call it as higher level language. Okay, means which can be understood by the human. Okay, like we are using some English words, right? But in case of computer, okay, they are able to understand only the binary language. Remember, only the binary language. If you are writing printf, I tell you, if you are writing printf, for the printf there will be some, like we are using some standard libraries. Remember that, okay, standard input output libraries over there. So they will be having a binary representation for that particular printf, which state the processor that you need to print this content which is there inside a double quote of a printf statement. Clear? Likewise, each and every instruction or each and every line, whatever you are writing in your program, it should be converted for the binary representation. Remember this. It should be converted for binary representation. But between that higher level language and a binary representation, intermediate, we got someone called as a assembly level language. I repeat, we got a higher level language which we are able to understand, and we have a binary language which is system can understand, which like a system can be able to understand binary language. In between this, we got a intermediate one, we are calling it as assembly level language. Intermediate. Okay, if you expand or if you elaborate the meaning of that intermediate language, then it will elaborate it as the higher level language. Remember this. Okay, so here we got some sample of this kind of language over assembly level language. See, in computer organization we are not using any kind of higher level language. Remember this, we are using assembly level language, a symbolic representation of a higher level language, or a symbolic representation of a binary language, we call it as. Yeah, okay, so here I had mentioned two examples of an instruction. Okay, just observe. Add a location a comma r naught. Okay, the first one is what? Add location a. Okay, we don't have a space over here. Sorry, location a. Okay, this is what the address of one particular operand. Operand means data exactly. Comma r naught. Second example. Add r1 comma r naught we have. Right? Okay, fine. How it will be executed, I will tell you in next slide. Okay, but now add a location a comma or not. What exactly this is? Okay, how many different contents we have? So here we got total 3 different contents over here. Okay, in this instruction also we got total 3 different content over there. See, first one what we have, add we are having, right? First what I have, add we are having. So this we are calling it as operation. Okay, this we are calling it as operation. What should be performed for location A and or not? Okay, it is specified by this operation exactly. What I need to perform? Add I need to perform. Okay, then what does this location A stand for? See, remember, okay, in the first class itself, I would like to mention the subject name is what? CO, right? Computer organization. Okay, so a formula is what? Chetan will go to office. Remember this formula. Chetan will go to office. Office will not come to Chetan, right? Okay, now online facilities available. Okay, but physically, if Chetan want to go for a office, okay, then what? Chetan should travel to office, right? Okay, so C will go to O. C will go to O. Okay, why I am saying this? Because okay, in our instruction we are having this fashion. Okay, source comma destination. Remember this, source comma destination, computer organization. Source should go to the destination. Destination will not come to the source. Remember this. Okay, I hope you got it. Okay, Chetan will go to office means source will go to destination. Okay, fine. Remember this. Okay, fine. Now, see here, if I consider source comma destination, so the original syntax of our assembly level language will be what? First, we'll be having a operation, okay, space, source will be available, comma, destination will be available. Operation, space, source, comma, destination. Okay, so this operation will be performing its original principles over the source and destination. Like that it is. Very simple. Okay. So here also, see, add is the operation, source is R1, destination is R0. Clear? Fine. Add is the operation, location A is the source, R0 is the destination. That's it. Okay, nothing else. Okay, fine. Now, uh, what does this location A stand for? Okay, or else what does this R0 stand for? Which are allowed to mention in the place of source, which are allowed to mention in the destination? That is what the big question now. Okay, see, some memory location should be mentioned in the place of source and destination. Remember this. Clear? We are not able to mention, or we are not supposed to mention the original address. Remember, I repeat, we are not supposed to mention the original address value of a memory location. Remember, okay, we may be having a original address locations like 0, 4, 14, 16, okay, 20, 24, 25. So these are the maybe the address number of one particular location. We are not allowed to specify like add. See here, we are not specified. We are not allowed to specify like add 16 comma R0. This is wrong actually. Okay, this states something different. Okay, in further classes we'll discuss. Okay, what does this stand for? Okay, so what we are allowed is we are able to mention, okay, address label. See, if I want to mention this location 16, what I need to do, I need to label this 16 as some other symbol. Okay, let me label it as location A. Okay, if I want to add the value of, or else the content of memory location 16 to R0, directly I should not mention the address 16. What I need to do, I need to label it as, I need to, or else you can name it as rename. Okay, we need to rename this 16 as a location A, and this location A should be specified in our instruction. Remember this. Okay, it is very important. Okay, so this is what the syntax what we got. Okay, now let me take this example. Okay, fine, and I will explain the next slide. Fine. Add location A comma R0. Remember this example, add location A comma R0. Okay, so this is what the von Neumann architecture we call it, a von Neumann architecture, or else basic operational concept also we call it as, or else communication between processor and memory. Okay, communication between processor and memory. So this is what the processor we have, and this is what the memory. Okay, before I discuss this, I tell you the motto of this figure, or as the the final conclusion of this figure. Okay, this states the communication between processor and the memory. Okay, if observe it carefully, if processor want to execute any one instruction, Observe my words. If processor want to execute any one instruction, it should bring the content from memory to the processor and later it should execute. Okay. Then after generating the output, sometime it will be just visualized, okay, for the user. Okay. Or else sometime it should be stored in the memory. Then what your processor will do, it will start storing the information back to the memory over there in any particular location it may be. Okay. So how processor communicate with memory means, okay, whenever we are trying to execute any one instruction, okay, those instructions should be brought from memory to the processor, and inside the processor we are going for different operation. Okay, so execution will be done, result will be generated. This is how the processor used to communicate with the memory. Okay, this is what the main motto of this particular figure. Clear how processor communicates with memory exactly. Okay, now we'll see the components. So here we got a memory. This is what the processor. Okay, inside memory, like we are not representing whether we are communicating to the primary memory or whether we are communicating to the secondary memory. Okay, for time being, you consider like you are communicating for the RAM. Observe my words. You are communicating for the RAM. Okay, in the back end of the RAM, obviously RAM will communicate to the hard disk. Okay, from a hard disk itself we need to get the content, remember this. Okay, but here we are not showing, just time being consider like we are communicating, processor is communicating with the RAM. Okay, fine. Now, okay, so for the first component of this figure is memory. Okay, then the second component is processor. So inside the processor we got sub components like MAR, PC, IR, MDR, R0 to Rn-1, control and ALU. Control and ALU we already know. Okay, like arithmetic logical unit for arithmetic operation, control unit for generating the write or read signal. Bidirectional we are having. This observe here. Okay. Whenever like the time comes, if you want to read command will be sent. If you want to write into the memory, write command will be sent over there. Okay, that's it. Then what about these 5 different shortcuts we are having? See here, MAR. Okay, what does this MAR stand for? Okay, here we got. See here, MAR stand for memory address register. Okay, MDR stand for memory data register. PC stand for program counter. IR stand for instruction register. Okay, R0 to Rn-1 we are having. This we are using it for like general purpose register, temporary storage it is. Arithmetic logical unit, control unit we have. So these are the full form of those components exactly. Now, what exactly this PC stand for? So I would like to begin with PC because this is what the initial invocation of this processor. Okay, from PC itself we are invoking the process. Okay, PC stand for program counter. Remember, very simple. It will be holding the address which should be accessed in the future. Clear? See, observe my words. If processor is busy with executing one instruction, the address of that instruction is 0. Consider like the address of that instruction is 0. Now processor is busy with executing the instruction which is located in a 0 over there. Then in future, the next line, if processor want to execute, then what should be the address of the next instruction? 0, 1 it will be, right? Okay, exactly it is not 1. If you are using a 32-bit system, address will be 0, 4. Difference will be 4 exactly. But now you consider like first instruction is in 0, second is in 1, 2, 3, 4. So these are the different addresses we are having. So now if processor is executing a instruction which is located in a memory location called as a 0, then which will be the next instruction processor should execute? 1, right? So that 1 will be targeted by the program counter. Program counter is responsible for holding the address of the future instruction. Remember this. Okay, program counter is responsible for holding the address of the instruction which should be executed in future. Clear? Okay, then what exactly MAR will be holding? Okay, this is what the future, this will be the current. Okay, what instruction you want to execute right now, that address will be held by or held by your MAR. MAR stands for memory address register. You may ask, from where MAR will receive this current address? Okay, from program counter itself. Remember, see here, like MAR will be holding the current address. PC will be holding the future address. If you are done with executing the current instruction, okay, then the future address, whatever we have, that will be transferred for MAR. He's having future, he's having current. Okay, after executing the current instruction, okay, if you want to go for the further, then we need next instruction, right? The next instruction address will be transferred from your program counter to MAR. So this is what the communication we are having. Future will be found by PC, okay, and the current will be or else future will be found by PC. Okay, once MAR become free, this address will be transferred to MAR. Okay, program counter to MAR. I hope you don't have any doubt. Clear? He'll be holding the future, he'll be holding the current address. Okay, what you want to execute, what processor want to execute. Okay, once that execution begins, remember this, once the execution begin, the current address will be erased. Current address will be erased and the future address will be uploaded for MAR. Now that future address has become current address. Then PC will be pointing for number 2. The first it was 0, PC is pointing for 1. Okay, after executing the 0, PC will be transferring 1 to MAR. Now PC will be targeting for 2, then later 3, then later 4, 5, 6, like that. Increment, that's it. Okay, line by line we need to execute, right? So we are incrementing the program counter so that we can target for the next instruction. That's it. Okay, so now PC is pointing for future, MAR is pointing for current now. Clear? Now, instruction register we are having. What does this instruction register stand for? Okay, I told you, right? We have an example of add location A, comma R naught. Okay. Out of that, there are 3 sections. First one is operation. Rest of 2 are operand. Operand means data or else data location, we call it as. Okay. So that second 2 locations, whatever we are having, like source and destination, that does not matter for instruction register. Okay, instruction register will be holding the operation instruction. Remember this, instruction register will hold the operation instruction. According to my example, add is the operation. So regarding the add, whatever the binary code we have, that will be held by your instruction register. Clear? PC is holding the future. Okay, and MAR is holding the current instruction, and instruction register will be holding what operation we want to perform. Regarding that binary code will be held by your instruction register. How it will be holding, we'll see that later. Okay, don't worry, I will explain. Fine. Now, if it is say, okay, fine, later, MDR and MAR we are, sorry, MDR we are having, right? MDR we are having. What does this MDR stand for? Memory data register. Okay, so whatever you want to read it from the memory based on the control signal, whatever you want to read the memory content, okay, so that will be through this channel itself. Okay, we call it as download and upload. Okay, while reading the content, memory will start uploading the content to the MDR. Okay, while writing the content, we need to write, or processor need to upload the content back to the memory over there. That's why we are having bidirectional reading the content from memory, right, writing the output to the memory over there. So MDR is a junction. MDR is a junction. Clear? Okay, it have other principles also, or as other operational concepts also. I tell you later while explaining the example. Clear? MDR is a junction between memory and the processor. Whatever you want to read, that should be uploaded for a MDR. Whatever you want to write, that should be uploaded for MDR itself. Okay, because we are having bidirectional over here. Clear? Then general purpose registers we are having, R naught to Rn-1. What does this stand for? Okay, N general purpose register. So these are the temporary storage. Very small amount of memory will be allotted over here. Okay, so this we are also calling it as primary cache. Okay, which is a temporary storage which is residing inside the processor. Primary cache, which is outside the processor, we are calling it a secondary cache over there. Okay, this is the memory which is very close to the processor. See, this is what the circuit of a processor, and the temporary storage is inside the processor itself. Okay, for like for generating the output or for completing the task. Okay, I repeat, for generating the output or completing the task, we may need some temporary storage location to hold the partial results. I repeat, to hold the partial result. That is not the actual result, partial result. For that, we are utilizing this R0 to Rn-1. Okay, so this is what the explanation regarding the components of the processor and the memory. Okay, now we'll see by taking an example like at location A, comma R0. We'll see how this will be executed. Okay, so consider like in 0 location some instruction we had. This is what the 1, this is what the 2. Okay, here also some instruction we have. Now your processor is busy with executing a instruction which is located in a location called as 0. Now MAR was holding 0, right? Okay, MAR was holding 0. Once the execution begins, I repeat, once the execution begins, we need to swap the content between program counter and MAR. I repeat, when the execution of this particular instruction which is located in a location called 0 begins, okay, Then we need to have a swap between the content of program counter and MAR. Previously, MAR was holding what? 0. Okay. Program counter is holding for 1 exactly. Okay. Once the processes start executing this particular instruction, okay, we need to have a swap. Okay. Or else the like program counter should exchange program counter should exchange the content with MAR over there. Okay. Now, okay, fine. Now, MAR will be holding the address called as 1 and PC is holding the address called as 2. Any doubt? Any doubt? Means once the instruction which was located in a 0 begins, okay, begins, then we need to update the value of MAR and we need to update the value of program counter also. Right? Okay. Now, next instruction, okay, which we want to fetch, okay, that we need to target. Fine. Now, after executing the complete instruction which was located in a 0, okay, now MAR, which is holding a value called as 1, so this should be uploaded for the memory. This should be uploaded for memory. Now, what memory is going to perform is, it will start looking for a address location called as 1. Okay, the value which is uploaded by the MAR was 1. So after receiving the value 1 by the memory, what will be the job, next job done by your memory? It will start looking for a memory location address called as 1. Okay, it will start searching for the cache. If it is available, from that itself it will upload to MDR. Okay, or else if it is in main memory like RAM, it will upload the content from RAM. If it is not at all allowed in cache and RAM, okay, it must be available in your secondary storage hard disk. So from hard disk it will retrieve the value, okay, which is residing in this particular location. That is nothing but add a location A comma R0. That is what the value, okay, we are targeting for. Okay, so your memory is looking for the whole content which is residing under a memory location called as 1. Okay, the memory will find what content is available inside that address and it will start uploading it for your MDR. Okay, target this location, find it. So whatever the content you have in a location 1, that is add location A comma R0, okay, should be uploaded for MDR. Should be uploaded for MDR. Now here, what we need to do is, we need to go for categorization. We need to go for categorization. In this instruction, what we have? We have add, okay, then location A we have, then later R0 we are having, right? Okay, please adjust with the handwriting, okay, because I'm unable to write a proper instruction over here. Okay, so complete content from the memory will be uploaded for MDR. Now, categorization for what? The first half is called as an operation, right? Second is called as a source, and third is called as a destination. Now, whenever we find this kind of operation, what I need to do, that operation should be transferred it for instruction register. Remember this, when we receive the content of a particular memory location into MDR, we need to go for a categorization. Okay, we are categorizing it as operation, source, and destination. Clear? Okay, now MDR should transfer that add instruction to instruction register. Should transfer this add instruction to instruction register. Now instruction register have, consider like we have some binary code for add like 110011. Okay, so this is what the binary representation for add instruction. Consider like, okay, just an example. Okay, then later location A. Okay, so while transferring this location A, see, this is what the source address exactly. Location A is a label of one particular address. I tell you, location A is a label of one particular address. So your memory, while uploading here, okay, your memory will also find that, okay, what is the original value stored inside a location A? What is the original value stored inside a location A? Consider we are labeling that location A for a location called as a 16, okay, in your memory. So inside this memory block 16, we have a value called as 5. Consider like this. Okay, so what is the label we have in our instruction? Location A, right? Okay, so your memory will start searching for a label called as location A. Yes, it has found. Okay, location A is found at location 16. Okay, then inside that what value we have? We have a 5. We have a 5. So 5 will be transferred for MDR. Clear? 5 will be transferred for MDR. See, location A is a label of some particular location. Okay, so inside that, what value we are residing with, that value should be uploaded for a MDR by your memory. Clear? Okay, like when we are discussing the module number 3, you will be having better knowledge about this. Okay, don't worry about that. Okay, so here location A, which is inside that with some value is residing. What is that value? 5 is the value residing. Okay, in a location called as 16. So 16 will be uploaded over here. Okay, it will be like binary code followed by a value called as 5 and followed by R0 exactly. Okay, now you may ask, what does this R0 stand for? R0 is a destination. That is nothing but your general purpose register. Why memory will not mention any value for this R0? Because R0 is not at all defined under memory. Remember this. It is defined under processor. It is defined under processor exactly. Fine. Okay. So now what we have, binary code of add instruction we had, that will be transferred for instruction register, and we got a value called as 5 inside the memory address, memory data register. Okay, now if I want to apply, or if I want to execute this add location A comma R0, so this 5 should be transferred for any temporary location. Okay, so that addition can be computed. So what I need to do is, or what your processor will do is, okay, R0 is reserved for the destination, so we cannot touch them. Okay, we cannot touch the reserved register. Okay, in this instruction itself, remember, okay, in this instruction R0, I am reserving it for the destination, so I should not touch, or I should not upload the value 5 for the R0. See, R1 to Rn-1, we have a free register. You can choose, or your processor can choose anyone. Okay, so we'll take example like processor will choose R1. Okay, so the 5 will be uploaded for R1. Okay, now R1 is made as a source and R0 is made as a destination. This is internal arrangement. Remember, this is internal arrangement of a processor. Yeah. So here what I have, here we have add instruction. Here we have a source. The value of source is 5. Okay. And one more thing, like inside the R0, already some value is residing. Consider like, okay, some previous operation. Okay, we are already residing some value inside the R0. Okay, consider like which is having 4. Okay, which is having 4, value 4. Okay, then arithmetic and logical unit will be invoked. Okay, we have instructions. Yeah, we have a complete operation instruction over here. We have a source, we have a destination. Then what I need to perform? We need to perform the arithmetic operation. That's it. So ALU will utilize the operation binary code, whatever we have inside the instruction register. It will apply this operation code over the source and the destination. Okay, now the question is, okay, after execution of add location A comma R0, okay, what will be the value of R0? Okay, destination value will be overrated. Remember, previously it was 4. Now it will be overrated as 9 exactly. Overrated as 9 exactly. Source value remains same. Remember, always source value remain same. Destination value will be overrated. Clear? I hope you don't have any doubt in this read operation. Very simple. Program counter will be holding the future address. It will be transferred for MAR. MAR will send it for the memory. Memory will start looking for that particular memory location. Yes, it will find. It will start uploading it for MDR. Okay. So now after receiving content for the MDR, categorization will be there. If it is the operation, it will be transferred for instruction register. If it is the operand like data, it will be transferred for general purpose register. Then arithmetic logical unit will utilize the instruction register content over source and the destination. Then result will be generated. Clear? Now this is how we are reading the content from the memory inside the processor. Now if you want to store the value back to the memory, example, if you are having like move, okay, move R0 comma sum. Okay, R0 comma sum. Okay, move R0 comma sum. Previously what I had, add location A comma R0. R0 is having a value called as 9. Okay, so this should be shifted for some location which is labeled as sum now. Okay, how it can be done? Simple, same. Okay, so the next instruction which I need to execute, okay, that will be targeted by the program counter. That is nothing but this instruction. Okay, so that will be transferred for MAR. Okay, again we are transferring it for the memory over there. Okay, meanwhile, observe here carefully. Meanwhile, okay, source is what? R0, right? Source is what? R0. So value of R0 should be uploaded for MDR. Now MDR consists of what? 9. Meanwhile, your control signal should be right. Your control signal should be right. Clear? Okay, so we want to move a value of a source to a location which is called as sum. which is called as sum. Now, the job of memory is what? It should find a location called as sum. That's it. It should find a location called as sum. Okay, found. Already it is found. Example. Okay. Then for this particular location, I need to write a value called as 9. Why I need to write? Because the control statement we are having is right over here. Yeah. Okay. So this is how your computer or else processor execute a single instruction. Yeah. So if you have any doubt, you can contact me. Fine. This is very important question. Okay. Thank you, students.